In this video, we now want to look at the complex plane, also known as the Argand diagram. This is a plane proposed by J.F. Argand in an attempt to represent a complex number on a plane. Just like we can represent a real number on a straight line, we have a real number line, a horizontal, then you start putting on numbers there, right? So, in a similar way, for complex number, we can actually show it on a diagram. It's a plane known as the Argand diagram, or simply the complex number plane. Now, with these diagrams, just like we have them on this side of the board, we can actually be able to determine what we call the argument of the complex number, in short, Argz. That Argz is also known as the polar angle of the complex number. Please put this down. What is the polar angle? What is the Argz, argument of Z? That is the angle measured from positive x-axis, take note, anti-clockwise, that is counterclockwise, down to the line of the complex number. Does that make sense? Always remember that you measure this angle from positive x-axis anti-clockwise down to what? The complex number line. Then you stop. It's just similar to what we learned from physics in one of our previous classes under vectors, where I told you that the angle of a vector is generally conveniently measured from positive x-axis, then you turn anti-clockwise down to the line of the vectors. You stop. That's how we get the angle of a vector. The same thing applies to this argument of Z, known as the polar angle. Now, there are four possible cases or diagrams that can be obtained depending on the value, the sign, depending on the sign of x and y in the complex number. So let us quickly go through them here. We'll have the four cases here. Case 1, you can say that z equal to x plus iy. So there, x and y are both positive. Of course, if you have to plot a graph, it's just like, trying to plot x and y. If x is positive and y is positive, you know that the point will be located between positive y and positive x. The first quadrant. Are you getting me right? So all you need to do now, the complex number line will be drawn from the origin in that first quadrant. You can see that, which I use z to represent. Now, to get our polar angle for the first quadrant, you can see, measure from positive x-axis down to the line of the complex number. That is theta, and it is equal to argument of z. So simply, for any complex number located in the first quadrant, the argument of z is simply equal to theta. And in this first quadrant, look at it, to get theta is simply tan inverse of the vertical axis y over the horizontal axis x. Tan inverse of that. Is that okay? Because of this right angle triangle, which we're going to extract. Case 2. When the complex number is equal to minus x plus iy. So you see x is negative, y is what? Positive. Once again, if you have a negative value of x and a positive value of y, if you plot such points in the plane, you're going to see it between positive y and negative x. That is the second quadrant. So you can see the location of the complex number z here. Is that okay? Once again, take note of the argument of z. Theta is measured from positive x-axis anti-clockwise down to the line of z, and then it stops. Theta, then, which is equal to argument of z. How do we get it? Watch. It's equal to 180 minus alpha. Now, alpha is this angle between this complex line and this negative x-axis. You can see that, right? And for us to get alpha, once again, we are going to use alpha equal to tan inverse. You can see that. In all, alpha is equal to tan inverse of y over x. So you drop your vertical, you get a right angle triangle, and then what do? You take your tan inverse of y over x. You get your alpha. Once you get your alpha, subtract that alpha from 180. Whatever value you get is your argument of z. The reason being that from this positive x to negative x is 180. Out of it, you know alpha. You are looking for this value. So it will be 180 minus what? Alpha, and you get your argument of z. Quickly, let us look at case 3. Z is equal to negative x, negative iy. So both x and y are negative. If you plot such point, you will notice that the point will be located in the third quadrant. Therefore, our complex number will be in the third quadrant. What is the argument of z? You measure from positive x-axis down to the complex number line. You can see. Is that okay? But then you notice that the complex number made an angle alpha with negative x-axis. So you need to get that value alpha. Once you get that value alpha, you take note that this angle from this positive x-axis down to the line of the complex number includes alpha as well too. It includes alpha. You need to step down this to get your right angle triangle, which we use in calculating alpha. Once you get alpha, add it to 180. You get your argument of z. You get your polar angle theta. Of course, because from positive x-axis to negative x-axis is 180. Out of it, the polar angle still stretched. It still moved into the third quadrant, adding up alpha to it. So whenever you have a case where the complex number is located in the third quadrant, it is 180 plus some angle called alpha, you now get your polar angle theta. Is that okay? That's argument of z. Case 4. In this case, x is positive, y is what? Negative. If you plot the point, you will notice that it will be in the fourth quadrant. So the complex number line is located in the fourth quadrant. Once again, look at your argument of z from positive x-axis down to this line of the complex number. So all you need to do, please I need to correct up something here. This is your alpha, not theta. I'm using theta to be the argument of z. That is the polar angle. So this is alpha. Good. So all you need to do is to calculate your alpha here using this right angle triangle. Then to get your argument of z, subtract alpha from 360. Because if you look at this whole thing, it's a complete circle, including what? Your alpha there. So if you subtract alpha from 360, the remaining angle will be from positive x-axis down to the line of the complex number you start. And that gives us our what? Argument of z, the polar angle. Alright, take note of this, that in all of these cases, alpha is equal to tan inverse y over x. Alpha, that angle you need to get. Then either subtract or add it to some other value to get your argument of z. Of course, notice something in the first quadrant. There is nothing like alpha there because this is already the first quadrant. If you draw, your polar angle would already be from the positive x-axis down to the line. The right angle triangle formed here includes that polar angle, argument of z directly, so you don't have any business with alpha in case 1. Modulus of a complex number. How do we get that? Simply use Pythagoras theorem. You know that this line is z, and it is the hypotenuse of this right angle triangle. So to get the magnitude of z, which is also known as modulus, which is also known as length of the complex number, it is simply z squared equal to y squared plus x squared. So to get your z, the magnitude, the modulus of that complex number, you take square root. Of course, this formula is something we're already used to. In the next video, we're going to pick questions and then solve. Get the magnitude, get their argument. We have a very first question here under complex plane or Argand diagram. In this question, we are asked to show minus 2 plus I on the complex plane and find modulus of minus 2 plus I, then argument of z. Take note that this minus 2 plus I is the complex number, so we can simply write z is equal to minus 2 plus I. So we have to show that on the complex plane. What do we do? So let's see that we're given z to be equal to minus 2 plus I. Take note that the real part gives us x. You know, this is the same as x plus iy. So you agree with me that x is equal to minus 2 and y is equal to invisible 1. That is the multiplier of I. Would give us y. Is that okay? Fine. Now we're going to draw the complex plane, the Argand diagram, and then show this. So I've got my axis. We have x to be a negative value, so that's going to be on the negative x-axis, and y is positive value, so this is positive y. Alright, so you see that the complex number minus 2 plus I is located in the second quadrant between positive y and negative x. So all I need to do is draw something like this. So this is my z. This is my minus 2 plus I. Alright, I've shown this on the complex plane. That's the solution. If I want to do further things, I can just decide to show the argument of z. This is theta, which is equal to arg z. And of course, you know to get it, since it is the second quadrant, already you know that this part is alpha. So you can drop this and calculate the value of alpha using tan inverse. Alright? So this is going to be 180 minus alpha to get the argument of z. Remember, we have the second part of the question there where we have to calculate the argument of z. I guess we have done a pretty good job on this showing of minus 2 plus I on the complex plane. I've even added certain extra information. Okay, now let us look at the first part of the question where we have to calculate the magnitude of z, which is the same as the magnitude, also known as modulus. Alright, modulus of z. And of course, to obtain that, you know from Pythagoras' theorem is equal to square root x squared plus y squared. So the modulus of minus 2 plus I is equal to square root x is minus 2, so I'm going to enclose that in bracket and square it, plus y, which is 1 squared. This minus is of no use. Minus 2 all squared will still give you positive. You would recall that I told you something in one of our classes in physics. Is that okay? Under vector specifically, that if you calculate the magnitude of something, magnitude, modulus, length, they are the same thing. The magnitude is always a positive result, so you don't really need to stress yourself putting negative there when solving. Alright, let's see what this is going to give to us. So the modulus of minus 2 plus I is going to give us, work out this and you would get root 5 as your solution. Root 5. So we're done with the first part of the question. Let us now move on to the second part of the question where we are to calculate the argument of z. For this problem, we've already established that at z is equal to 180 minus some angles, which is what? Alpha. So we're going to get alpha. How would I get it? Let's extract the right angle triangle from which we would obtain the alpha. All this I'm just showing is for you to see the full solution. In subsequent questions, I wouldn't bother extracting all these facts. We just go directly to solving the problem. Now, the x value is minus 2, the y value is 1. So you see, we can get our alpha from here. Alpha is simply tan inverse of y over x, which is equal to tan inverse of 1 over minus 2. The negative sign is of no use to us. Is that okay? It is the whole value that we want to get. If you obtain tan inverse of 1 over minus 2, let's see what we're going to get. Tan inverse of 1 over minus 2 is given minus 26.56. But like I said, we're only interested in the positive result because we're trying to calculate the argument, the value of the angle. So this is going to be 26.57 approximately in degrees. It implies that argument of z at z is now 180 minus 26.57. What would this give to us? Let's find out. Argument of z is now equal to, so we're going to have 180 minus 26.57. 26.57. So that's given me 153.43 degrees. Now I want to show you something. This 153.46 degrees can be converted to degree and minutes. What do? Just pick 0.43. This 0.43 is the same as 0.43 and multiply it by 60. Multiply by what? 60. So I'm picking 0.43 times 60. And from here it's giving me 25.8. That 25.8 simply pick the whole number part, which is approximately 26. So this is going to give us 153 degrees. In fact, 25. Because we're picking just the whole part, 25 minutes. Does that make sense? Therefore, the result can either be this 153.43 degrees or it can be 153 degrees, 25 minutes. So that is the argument of z for this question. Now, we have this next question on the board. Let's look at the question. Express z equal to minus 4i minus 4 in polar form. Now, at the end of what I'm going to solve here, as you follow along, you have to test your zone of proximal development by writing z equal to 7 plus 7i in its polar form. How do we approach this question? Don't you think it's wise for us to even know what the polar form of a complex number is? And of course, to do that, I am delighted to inform you that in one of our previous classes in physics, vectors specifically, I already pointed out the concept of polar form of the Cartesian form of a given displacement. Of course, we stated that once you have the Cartesian coordinate, which is where we deal with all these x and y, z equal to x plus iy is the Cartesian form, the rectangular form of complex number. That x and y can be converted to cos theta and sin theta respectively. You still remember that, right? Good. So when you're dealing with the polar form of a given coordinate, all you need to do is to get theta, the angle that the complex number made with the positive x-axis, the polar angle, the argument of z. Then simply write cos theta sine theta. That cos theta is the x value. That sine theta is the y value. Where each of them will be multiplied by the magnitude, the modulus of that complex number. That's just all you need to do. So this is the complex form. Alright, now in the question we're given z to be equal to minus 4i minus 4. Now the polar form, take note is equal to, is in the form x plus iy, where x now is minus 4, the real part, and y is minus 4 as well. So the polar form is, that's the polar form of a complex number is giving us z equal to modulus of z, open bracket, cos theta, then plus I sine theta. So you're expected to memorize this. Is that okay? Actually, it is derived from considering trig identity for right angle triangles, sine and cos, right? So this is the polar form place. Memorize it. So whenever you are to write anything in polar form for complex number, you need to express it in this form. So all we need is to get the modulus of z, that's the magnitude, and then we get the polar angle, which is the argument of z. In fact, let me indicate it. Theta, where theta is equal to arg z, or polar angle. Polar angle. We already explained that concept. So let us quickly do this. Is that okay? Now, must I sketch this diagram? I really don't think I need to sketch it. From the outset of this complex plane, I already showed you 4 different cases, helping us to locate the position or quadrant of the complex number depending on the sign of x and y. You notice that y, the coefficient of I, is minus 4 and x also minus. Therefore, this z is located in the negative quadrant of x and y axis. So, that being the case, it means it's going to be in the third quadrant. The third quadrant. Okay, let's go for magnitude of z first. Magnitude of z is square root 4 squared plus 4 squared. I've told you I didn't want to have any business with the minus, knowing that the magnitude will still give me a positive result. Is that okay? So this is going to give us a square root of 32, because this is 16, this is 16. According to sort, this square root of 32 can still be written as 4 root 2. Is that okay? 4 root 2. You can still write it in this form. 4 root 2. You know that using the principle of sort. Okay, we've obtained the modulus of z. Let's now go for the polar angle. Now, to go for the polar angle, what do you need to remember? The diagram for this. So just assume that you have the diagram upstairs, you have it in mind. So what are you going to do? All you need to do is to start working on it. Take note that x is negative and y is what? Negative. So at z, which is equal to theta, will be equal to 180 plus alpha. Are you following, right? In the third quadrant, you're going to add that angle alpha to it. And how do we get alpha? But we know that alpha is equal to tan inverse of y over x, which is equal to tan inverse. Y here is minus 4 over minus 4, which is the value of x. So alpha is simply tan inverse of 1. Tan inverse of 1. Tan inverse of 1 is going to give us what? 45, I guess, right? Let's find out. Tan inverse of 1, correct, is giving me 45 degrees. Which now means that theta, or at z, argument of z, which is equal to theta, will be 180 plus 45. And 180 plus 45 should give us what? They're about 225, isn't it? Let's see, 225 degrees. Good. So we now need to write this in polar form. Therefore, z is equal to magnitude of z, and the magnitude of z we got it as root 32. If you want to use 4 root 2, the choice is yours. Of course, if it's an objective case, it depends on the option given to you. Open brackets, cos theta, and theta is 225 degrees, and then we're going to add it to I sine 225 degrees. This is our result. Is that okay? This is our result. This is our result. But of course, we can still write the result in another form. Or, let's do something. We can say that z is equal to root 32. I want to convert this theta in degrees to radian. How do you convert from degrees to radian? Simply multiply the degree given to you by pi over 180. You can put all these down, alright? Make sure you make a note of it. So I can say this is cos 225 times pi over 180. That's to convert the degree to radian. Is that okay? 180 then plus I sine 225 times pi over 180. Pi over 180. If you work on this, what are you going to get? You will notice that z will now be equal to root 32. Then open bracket cos 225 divided by 180. What can go? Let's find out. Let's find out what can go. 180 divided by 5. 5 can go through that. If I have 225 divided by 5, that's giving me 45. Then 180 divided by 5 is giving me 36. 45 and 36, 9 can still divide that. I hope you know that, right? So I guess this 45 can actually do the division for us. 225 divided by 45 is giving me 5. So this is going to be 5 all over 180 divided by 45. 180 over 45 is 4. So divided by 4, pi plus I sine 5 over 4 pi. So this is another alternative answer to the polar form of z. Why this gives us the value of the polar angle in degree, this gives us the value of the polar angle in radian. Either of them is correct. And now we have this third question on the board, okay? Before we go into this question, did you take note of the fact that question number 2 drew our attention to the fact that there is this relationship between rectangular coordinate, also known as the Cartesian coordinate system, and the polar coordinate. Now, take note of this. You can put it down once again, please. When dealing with the Cartesian, also known as the rectangular coordinate, we deal with x, y. This can be converted to polar coordinate. When dealing with polar coordinate, we deal with the modulus of the complex number, the polar angle. That is simply z, theta. So one can convert between these two from one to the other and vice versa. Is that okay? And of course, that is why we've got this question here, because it's important for you to know how to convert from one of the coordinates to the other. I'm going to solve this third question, after which you test your ZPD by expressing 4 root 2, 225 degrees in Cartesian coordinate. But let's look at the one we have to do together. Express z, theta equal to 2, 2 over 3 pi in rectangular form, x plus iy. So you see this, right? From the question here, we're given the polar coordinate. The polar coordinate is the magnitude of z, which I simply wrote as z, and the polar angle, the argument of z, and the value is z, 2 over 3 pi respectively. So we have to write this in rectangular form, in Cartesian form, and then present the answer as x plus iy. It's a simple concept. Simply get your x, simply get your y from the z and theta value, then fix it into the rectangular coordinate expression, x plus iy. Let's do this and see. Z, theta, as given to us, is equal to 2, 2 over 3 pi. This simply means that the magnitude of z is equal to y, the polar angle theta, or at z is equal to 2 over 3 pi. Now we have to convert this 2 over 3 pi to converting it to degrees. Is that okay? To degrees, so that we can be able to evaluate it in degree. Are you following? How do we convert from radian to degrees? Remember, when we are converting from degrees to radian, we multiply by pi over 180. So to convert from radian to degree, you do the opposite. You're going to multiply by 180 over pi. Does that make sense? So this is going to be times 180 over pi. Now you would agree with me that the pi's will cancel. Alright, this constant will go off. And then 3 can go into 180. What would you get? 3 can divide 180, and that's going to give us 60. 60 times 2 would give us 120 degrees. Does that make sense? 120 degrees. Our problem is solved. Now, let's get x and y. But I might choose to write that the polar form is z equal to magnitude of z, open bracket, cos theta plus I sine theta. And then z is equal to, the magnitude of z given to us from the question is 2, then cos 120 plus I sine 120. Now take a look. 2 times cos 120 will give me the value of x. Are you following? And then 2 times sine 120 will give me the value of y. That's just a simple trick. I can just write that x is equal to 2 times cos 120 and y is equal to 2 times sine 120. Then you get your result in that form, x plus iy. Alright, let's proceed and see what this is going to give to us. Then this is 2 times cos 120 is going to give us what? Let's find out. Right, cos 120, I think that should be due about 0.866. Let's find out anyway. Cos 120, okay, that's minus 0.5 rather. Minus 0.5, then plus sine 120. Okay, sine 120, it's giving us 0.866. I'm going to multiply it by I, the imaginary number. So z is now 2 times this will give us minus 1. That's 2 times minus 0.5. Then we're going to add it to 2 times. 2 times 0.866. Here it's giving me 1.73. Okay, let's approximate 1.7 I. And we've expressed these in the form x plus iy. You get that right? So this is our result based on what the question says we should get. Answer. Please note that in this case, x could have been obtained simply this minus 1. X is equal to 2 cos 120. Then you get a minus 1. And then y is equal to 2 sine 120. Of course, that is going to give you approximately 1.7 value. So it's important you get to know this, alright? Please test your zone of proximal development with this question, alright? Test it. Already this is in degree, so you don't have problem. This is 4 root 2. Using the knowledge of surd, you know how to convert this mixed surd 4 root 2 to single surd. Then you simply put it in polar form, obtain your Cartesian coordinates. That is what we are asked to get. Okay, in this question, you were not asked to express it in this form. They just say get the Cartesian coordinates. So get the value of x, comma, get the value of y. That's what you're required to do in this your problem. In this video, we try to bring out a summary of what we should know depending on the quadrant that the complex number is found. Because just think of a case where you're seated for an objective examination, so you've got options to select, because you know you're working with time in your exam, you need to be as fast can be. And so do you think it's really ideal drawing the Argand diagram for any such question and then before you can determine the argument of z? Of course, it's really not ideal. That is why, as a summary, please, you want to have this in your mind. Just memorize these concepts we have here on the back. Okay, the first one is when z is in the first quadrant. Of course, in that case, both x and y would have positive values. And that being the case, it means that the argument of z would simply be equal to tan inverse of y over x. The argument of z in that case will be theta and simply tan inverse of y value over x value. That is in the first quadrant. Under a case where x and y will be positive there. Then in the second case, what if you're given a problem where x is negative and y is positive? You have it like this, right? Then we know that the location of the complex number is going to be in the second quadrant. Now, how do we obtain the argument of z there? Simply 180 minus alpha, where alpha is an angle that is obtained from tan inverse of y over x. So simply get the tan inverse of y over x, which is your alpha, subtract it from 180 to get theta, which is the argument of z. Does that make sense? Now, in the third case is when z is equal to negative x, negative iy. That is to say, x and y are negative there. We expect that the position of the complex number is going to be in the third quadrant. Because in the third quadrant, x and y are negative. How do we get our argument? Simply, all you still need to do, obtain your alpha, where alpha is equal to tan inverse of y over x. Then you can do 180 plus alpha. That 180 plus alpha is your argument of z, which is the same as theta, according to how I've decided to use my symbol. Of course, that is what we have here. Is that okay? Argument of z for z in the third quadrant is going to give us 180 plus alpha. Then, in the last case, that is where the location of the complex number is in the fourth quadrant. That happens when x is positive and y is negative. In such a case, simply do 360 degrees minus alpha, where again, alpha is equal to what? Tan inverse of y over x. Please always remember, in all, alpha is equal to tan inverse of y over x. Then depending on the quadrant that z is located, you can either add or subtract alpha from the angle 180 or 360. In the next video, I'm going to present to you what we should know about special angles. This will help us to evaluate certain problems, without needing calculator for special angles. That is coming up in the next video.